I'll talk about a very basic concept and a little bit of the application of this ultra-short echo time MRI techniques. So let's start. Okay, so here are the contents that I want to cover today. So I'll start from the basic physics. I hope you have some MRI physics background, but I'll start from the basic thing for UTE, and then to go over what kind of artifacts are associated with the UTE, and then some different approaches for UTE imaging, and then I will just show you some briefly about different contrast mechanisms for the morphological UTE imaging. So let's start from the basic physics. So yeah, so when you talk about, I think you already know about like a T2 and T1 or the relaxation about in the MRI, and then in the human body there are many tissues with actually the short TE. Let me turn on my pointer. Okay, so for example, like a ligament has like the T2, the below 10 millisecond, and then the bone, and then the tendon. They have very short T2 compared to the other soft tissues. So the conventional MRI cannot image that very well. So there are several challenges in the conventional MRI to image those the short T2 tissues, because the signal decays so fast in the T2, right? T2 decay. So we need to use like ultra short echo time to capture the signal, but the signal also is very low compared to the other long T2 tissues. So typically the proton density and then the abundancy is like much lower than the long T2 tissues, like less than 10%. And also the signal intensity is very low, much lower than the long T2 tissues. So in the conventional MRI, the short T2 signal is often affected by those like surrounding long T2 tissues. So we need to do like some suppression technique. So how to image the short T2 tissues? This is all about the UTE imaging, right? So this is very simple. Just use like the short TE, short echo time. So this the image on the left shows the typical signal decay with like a bi-component the tissues. So there are short component, and then they're followed by the long component. So it is the conventional echo time, which is like a few milliseconds in the gradient echo. So the short component, the signal is already the decay to near zero. So there's not much signal remaining for the short T2 tissues. So only long T2 the signal remains. So basically, by using the most significantly the shorten the echo time, for example, like 8 microsecond, then you can still get this short T2 component in the image. So this is the idea of this UTE imaging. Then, so let's start from the two most frequently used the sequence in MRI. So I think you already learned about this in the class, the Tom's class. So this is a spin echo, right? So after the 90-degree, the pulse, then we apply the 180 refocusing pulse to get the echo, like spin echo. And then to read out the data, we apply certain phase encoding gradient, and there's a rewinding gradient, and then the readout. So this process, this preparation takes a long time to get your image in the end, right? So, or your signal. So compared to the spin echo, so gradient echo, we just directly acquire the free induction decay signal just by using this the rewinding gradient and then phase encoding gradient. So TE is much shorter than the spin echo, but still not very short to capture these short T2 tissues, because the T is still like a few milliseconds. And then we want to image the tissues with the T2 star around probably below the 1 millisecond, like 300 microsecond or 500 microsecond, right? So we start from the gradient echo. This is the the conventional Cartesian, right? The imaging based gradient echo. So in each TR, so we apply this phase encoding gradient to get to your desired the KY direction, the KY coordinate, right, in the K space, and then to rewinder, right, and then to read out. And to read out each TR, you read out your K space in the Cartesian scheme, right? But this rewinding and then the this phase encoding part, this takes time. So that signal is already decayed to zero. So the simple approach is just remove those the gradient, right? And then we can shorten the TE. But now this is not like the imaging anymore. Like this is you just read out the data from center to the right, right? And but let's see. So what you can do, and then still we have this gradient for the slide selection and then the rephasing. So in the end, right, in the beginning, so that is still some long time for the UT imaging. So we want to remove that, but we still for the some case we want to do slide selection. So we use this kind of the half pulse. This basically you just use the half of this sync pulse. Then we need to actually do the data acquisition twice because this only covers half of your the frequency, the bandwidth. So we typically do the imaging twice with a different polarity of this slice selection, and then after a certain time, so in the from the end of the pulse, and then we cannot just directly read out the data because there is a certain called dead time. So after the RF excitation, so our RF system in the MRI, the scanner, is still in the transmission mode, and we need to switch it to the receiver mode. So there's a certain time, that takes to switch to different mode. So we call the RF dead time. So after RF dead time, then we can start readout using this kind of the trapezoidal gradient, right? But still, we only cover this one line in the space over and over and over. So what we can do is we can just rotate the gradient, right? Rotate the gradient in each TR and then cover the K space with this rotating gradient. So and then that gradient is just simply the linear combination of those the gradient, right? And then the linearly scaled gradient using this cosine and sine data with desired angle, right? Very simple. And then, so again, this is the typical UTE 2D UTE imaging pulse sequence. So again, after half pulse, and after that time, we perform this ramp sampling using the trapezoidal gradient, which is rotated over the TR to cover to the K space. So again, we use a half pulse, and then the variable excitation, the slide selection, the scheme called the pulse, and the ramp sampling, and then fast TR switching, which is like to shorten the dead time between the end of the RF excitation and then the beginning of the data readout. For 3D UT imaging, we can just simply use a non-selective, the hard pulse. So there's no slide selection gradient here, right? And then we can still do this center out the radial acquisition. So each spoke in HTR, we rotate that this spoke to cover this spherical K space, the 3D K space. So we can use also the slab selection, so using the special the half pulse too. And then everything is same, just only we use the gradient in 3 direction to cover the 3D K space. And also there have been many the trajectories. So far any question? So I don't see that the chat here, but if you have any question, just you can just feel free to interrupt. Okay. So there have been many trajectory proposed in the literatures. So this one popular trajectory is called stack of star. So it looks like a radial in the 2D, right? And then, but we covered 3D K-space using this kind of star, the stacked stars. So we call the stack of star. So I think this approach has some advantage because in the KZ direction, we can cover this with some kind of Cartesian scheme. So we use a phase encoding scheme in this direction. So the scan time is much shorter, and also the less affected by eddy current in the phase, because phase encoding is robust to the eddy current. So this is the one popular method. Also, another popular method is you call the UT cones trajectory. So that 3D K-space is covered by which means like the conical the shape, conical surface with a certain polar angle, and then we have the multiple cones, and each cone is covered by this kind of the 3D spiral trajectory, which rotates over TR. So this is quite efficient, more efficient than conventional 3D radial UTE, because we can use this the spiral trajectory. So this is very useful for the in vivo scan because the scan time is typically shorter. Okay, so let's come back to the radial UTE, which is the most popular technique for UTE imaging. Then how we can get the image, how we can get the image reconstructed. So let's say we have the center of the half radial projection, right? These circles are basically sample data. And then to get the image, we typically use this Cartesian-based the Fourier transforms. We call the inverse discrete Fourier transform. So we want to get the data samples in this Cartesian grid. So we need certain pre-processing, which is called gridding or regridding in the MRI. So this is very, very popular technique to get the image from this non-Cartesian trajectory. So this is one TR, and then we got the one spoke, and then the multiple samples in one spoke in one TR in this radial direction. And then what we want to get is we want to get this Cartesian gridded sample like this, right? And then the simple approach is just do the data interpolation. For example, we do the convolution. So we apply, for example, this kind of convolution kernel, and then at each sample we just put this kernel and then do convolution, and then estimate the data here in the Cartesian grid. So this is like this typical convolution the process. And then we do that for all the samples, and then we get the data in the Cartesian grid. And then you can just simply do inverse Fourier transform, then you can get the image, 2D or 3D. One thing we can do is because this sampling density, if you have multiple the line, sampling density is typically the much denser, so in close to the center of K-space, right? And the much sparser in the end of K-space. So we need to compensate for this different density, because this point in this grid, this point is much affected by convoluted by much less samples than neighboring samples. And for example, this sample is like convolved by the much more denser samples in the K-space. So we need to compensate for that. So this is a very important step. But this is very pretty standard MRI the technique to get the image from the Cartesian data. Okay, then so what kind of artifact can affect the UT imaging? So there are two major artifacts in the UT imaging. First one is eddy current induced artifact, and then the second one is called the shorted to star blurring effect. Okay. So eddy current, I don't know if you you ever heard about this, but eddy current is actually it happens everywhere. So if there is the changing the magnetic field, then you in the conductive material, there's the current generated, right, in the space. So, but also that can happen in the MRI system. So for UTE imaging, this is more problematic because we use non-Cartesian imaging. Also, we use a ramp sampling technique. So in the UTE imaging, so mainly caused by this slight selection gradient for to the UTE, and then also this ramp sampling. Then which means like this, we use this trapezoidal gradient, and then we do data result using all these the gradient, including this ramping part. So this can be a problem in UTE imaging, but this can be corrected if you can measure this effect using the certain special sequence or technique. But I don't want to go too much in detail for this kind of correction technique, but I just want to show the eddy current artifact, how can it affect. Okay, so eddy current can be actually modeled by certain convolution. This is convolution, right? And then the eddy current is actually a function of this how fast the gradient change, the gradient change in the time domain, right? And then this is also can be modeled by the impulse response, which is the weighted sum of this exponential decays with different time constant. For example, certain time constant like this exponential decay, and something maybe longer, slower, and then something much faster, and then this all the sum of this the exponential decay, because the MRI system is kind of very complex. It's composed of very complex hardwares. So each component can generate this single the eddy current, right, which decays in the exponential the scheme. So the net the eddy current is the kind of the weighted sum of these all different eddy currents in the MRI system. Okay, so this is the basic the model of this eddy current in MRI. Okay, and then okay. So for example, we have this kind of gradient, right? And then this one changes in the positive direction, right? And then say that this is the impulse response. Then we get this kind of the eddy current, right? So you see that this is always like the minus direction, opposite direction. And after that, when it's ramped down, then a current is generated in like this shape. And then actual gradient shape can be kind of the low pass filtered shape. So we never be able to get the exact shape that we prescribed in the MRI system. So we always need to deal with this kind of the eddy current effect. Also, yeah, so that's why the UTE imaging is more affected by this eddy current, because we want to use this ramping part of gradient, which is distorted by the eddy current. Okay, in terms of space, so eddy current can be in the space, like if you have the MRI scanner like this, then eddy current can be generated in the imaging subject, and also in the space, right? In the free space, the magnetic field can be affected by this eddy current. So that can be modeled by this kind of spatial harmonics. So the zeroth order means like in the space, so you have the constant the change of your gradient, your magnetic field, and then first order term that actually generates the magnetic field in the gradient, in the linearly changing gradient in the space, x and y, z. It just looks like a gradient, right? Gradient field in the MRI system. So there are also some cross terms and the higher order terms in the space, which is generated by. When I'm talking about the magnetic field, additional magnetic field. generated by this eddy current. So, but higher field, we can typically just ignore that because it's very small and then it doesn't affect too much in our imaging. But for especially for UT imaging, but for this lower order term, like a zeroth order and the first order term here, it's more that more affects the imaging. So we want to compensate for this error. So this eddy current induced the magnetic field, let's say the PE, is just approximated by the sum of this P0 term. We said zeroth order term, also called P0 eddy current, and then the first order term, which is also called the linear eddy current, because this one just look like a gradient field. So we can just say this is kind of additional gradient field that distorts your input gradient field. So again, the P0 eddy current cause the phase error in the global phase error in your all different spatial location, and the linear eddy current actually that causes the gradient distortion, because this is just imitates like the gradient field. Okay, so then, but let's talk about the linear eddy current, because linear eddy current is more problematic in the UT imaging, because again, that distorts gradient shape, which is critical for the imaging, right? So there are two different cases, right? Non-Cartesian imaging and Cartesian imaging, right? So if there is some gradient distortion due to the linear eddy current, then Cartesian imaging only is affected. Only the result frequency encoding is affected, right? Because the phase encoding is done by the linearly scaling the gradient. So eddy current is kind of we can assume that it's in the LTI, linear time invariant system. So if you linearly scale the gradient, then your error, the error can be also linearly scaled. So it doesn't affect too much in the imaging in the phase encoding, but frequency encoding is more affected in the Cartesian imaging. Just like so, there are some unwanted delay, right, like this, right? And then the non-Cartesian imaging is more like unexpected, because in the non-Cartesian imaging we don't typically use that the phase encoding gradient. Everything is like a kind of frequency encoding. So again, in the Cartesian imaging, if there is a linear eddy current, let's say, then for example, the sampling the location is kind of globally delayed, so like to the certain direction in the frequency encoding direction. Typically, that causes like this kind of the phase error in the image. But it doesn't really matter if you only care about magnitude of your MRI signal. But if you care about this phase information for certain MRI application, then you want to correct for that. But it's much easier to correct than the non-Cartesian imaging. You can just just correct for compensate for this like a group delay, right? And then if there is for example, there's a spiral imaging, right? And then if there is the linear eddy current, then your resultant image is more like it's unexpected. So you want to definitely to correct for this gradient error in the non-Cartesian case. And then in our UTE case, for example, radial imaging, and then if there is the uncorrected eddy current, then typically there's a certain misalignment between the lower frequency and then higher frequency component, which gives this kind of ringing artifact in the tissue boundary. So we want to really want to compensate for the eddy current for UT imaging. Okay, and then another the artifact, the very popular artifact in the UT imaging is called UTE. The T2 stop loading artifact. So basically, say, okay, this is the 2D UT imaging, and then we do the center out readout in each TR like this, right? TR, but for readout, it takes time actually. The readout typically takes time to get to this certain the case-based location. So this speed of encoding, or say that efficiency of encoding, depends on the readout gradient, how strong gradient, how fast ramp up the gradient, and then your hardware performance of the MRI system. So when you sample this single line, your the associated echo time, the tissue, short tissue, the signal decays like this. For example, this in the KY direction, right? So this signal decays like this, for example. Then when you get to your desired the case-based location, which corresponds to your desired spatial resolution, then there's no more signal remaining, right? So the case space is kind of modulated by this signal decay from your short tissue, right? So this looks like just like the low-pass filtering. So you have higher weighting, signal weighting in the center, and the lower weighting, so lower signal, right? Lower weighting in the periphery of your case space. So it's kind of, it looks like low-pass filtering. For longitude tissues, right, it doesn't affect much. But short tissue, again, it's kind of the low-pass filtering effect. So this is called the T2 star blurring. So this is a 1D simulation. So this T2 star blurring effect depends on encoding scheme, like how fast you can encode your case space, and then trajectory, and then your targeted tissues. So if you see like a tissue with a T2 star of 500 microsecond, okay, let's only see maybe frequency encoding UTE. This is a typical UTE. So this is a simulated 1D profile, which has not much, right? The blurriness. If you see this boundary, it's quite okay. But if there's a much shorter T2 star decay, then if you see here, this one has much more blurriness artifact. So just like there's a low pass filtering, okay? And what different the encoding scheme can improve that, but this is kind of unavoidable because the hardware performance of the MRI system, I mean gradient performance is not like infinite, right? This is limited. So this is another simulation, like a 2D simulation with typical UTE imaging parameter, right? Then this one color map shows encoding time. So red means like the later time delay, and then blue means 0. This is like a start of, right, the encoding. And then so I simulated this with a T2 star of 0.3 millisecond. So 0.3 is here, right? It's around like a yellow color. So that means, when we get this point from center to out, right? It's a yellow point. Our signal is already decayed to like exponential, right? Exponential -1, right? That is about 37%, right? So only 37 something percent remains at this point. And then we go further and further, and then decays to 0, the more, right? So this is kind of, it looks like the low pass filtering, because in the center you have higher signal, and then periphery you have lower signal. So you see that, right? This boundary, you can see that image is kind of blurred. But if you use like a much stronger gradient, without gradient, that means you can shorten this time to get to certain point, case space location. See that, right? Here I use like the much stronger gradient. You can clearly see that the blurriness is much more reduced. And then if you see the 0.3 millisecond area, right? It's right here. That means it much more faster. It encodes the case space much faster, much more efficient. Okay, so you can reduce the shortwave to stop blurring. So for UTE imaging, just to reduce this blurriness artifact, you want to use a stronger gradient. But again, as I said, there's some limitation in the hardware performance. Also, there also FDA limit for this gradient slew rate, right? Which is like 200 millitesla per meter per millisecond. So you cannot just go like infinite, even if your hardware allows. There's a certain limit, because if you change your gradient too fast, then that can generate eddy current in the human body that can stimulate the peripheral nerve. So we call that peripheral nerve stimulation, PNS. So that can cause the discomfort in the patient body. So some kind of twitching muscle and some very strange feeling. So if there are certain FDA limit. Okay, so far we just talked about this radial UTE mostly, which is the most popular technique. Then let's just briefly go over this. What are there any other approaches? Okay, this is traditional technique called like a single point imaging. So single point imaging is based on pure phase encoding in 2D SPI. We do the phase encoding in two directions, K, X, and Y direction. And then just like phase encoding, you go to right? And then encode this data point, just single data point in each TR. So again, so for example, this is a 1D case, right? So after RF excitation, so immediately after you get desired resolution, you encode one single point using this single gradient, and then you can linearly scale this gradient to get different data point in different case-based location. So this is very good because this is very strong to the eddy current. Again, this eddy current scales with this scaled encoding gradient, so it doesn't affect image quality too much, even if there's the huge eddy current effect. But this is very time intensive and very expensive technique. So yeah, it's not used too much, as it is in the recent time, but still, this is very useful technique for certain case. So SPI. And then another technique is called the ZTE imaging, the zero echo time imaging. So this is our typical UTE imaging, right? Right after the RF dead time, we do RAM sampling, right? But the one disadvantage is like this ramping part. This takes time to get the full the encoding efficiency. So the ZTE imaging is like, so there's some previous technique of the ZTE imaging called GLASS and Rufus that actually use the pre-ramped up gradient and then to RF excitation, and then we can encode the data with a full gradient efficiency, right? With a Gmax right after the RF excitation. This one too. This one, this is basically same as a blast, but the gradients are kind of the smoothly changing, which is good for the silent imaging, because this kind of the fast changing gradient can cause some acoustic noise. But this kind of concept can reduce the acoustic noise. So this ZTE technique is basically like this source two technique, but this is very good to get the shorty2 component, but it often limit the flip angle and then readout bandwidth, because we apply certain gradient during RF excitation, so that cause unwanted slide selection. So it's not controlled, but just like slide selection due to this the slab selection actually due to this effective gradient. So we typically use very low flip angle and low readout bandwidth. So it can be the low SNR, right? So this is just the simulated the encoding efficiency, encoding trajectory using the CTE, which is in the solid line, and UTE, which is in the dotted line. So CTE with a different like readout bandwidth, right, gives different the encoding speed. This is a time, right, in this direction. So this one shows like a very short, very fast encoding, which is not very feasible in reality. But so if you see this point, right? So it's dotted line is a UTE imaging. So the CT imaging does pretty good job in before like this is like maybe something like a 17% of your case space, the location, right? The case space trajectory. The CTE does quite good job. And after this point, UT does better job. So you want to use the correct, the good appropriate technique for your desired application. Because if you want to image something that has very shortly to start, then CT may be beneficial. Otherwise, UT may be more efficient. So there are two different techniques and two different advantages and disadvantages. Okay, so again, CT imaging has been used as like silent imaging by using this slowly ramped the gradient. But there's one issue that because again, we apply the gradient during RF excitation, and then after the RF dead time, right? You already it's outside of the central case space, something like this. But you're missing certain the central area because we start encoding after certain the location, right? Like this. So that it causes like this missing the spherical area in the central case space. So people have been using the WASP technique and then single point imaging technique to fill this missing data. I won't go into too much detail, but there are certain techniques using this CTE. And there are also some popular tech, not really popular, but there's a famous technique called the SWIFT. It's developed by Dr. Garwood, and then their group, I think they use this technique a lot, but it is not very often used in the MRI society. But this is very also very interesting technique. They use like a kind of the adiabatic the pulse using the hyperbolic sequence pulses, composite pulses, and then each set of the RF pulse is used to the encode the case-based projection line using the sweeping gradient. Here the gradient remains same, right? And then the frequency of this RF pulse is changed in this set. So yeah, I will not go into too much detail, but this one has also advantage of the silent imaging, but the SAR is quite high and then SNR is quite sometimes limited. So that's a disadvantage. And then their result, you can see here with the sweep, you can see this bone area, right? Bone signal quite well. And then there's also a technique called variable TE. This is kind of the mixture of this Cartesian and then non-Cartesian imaging. So basically, when you encode right this line with a KY equals to 0, then we don't need this phase encoding, right? So that means you can encode right after your rewinding gradient. You can just apply to data readout. So this is the shortest TE for this line. And then to encode this line above, right, in the KY, and you can use the very small phase encoding gradient, and then your TE is a little bit more delayed. So if you want to go further and further in the KY direction, then you want to use a larger the phase encoding gradient and the data readout point, right? The start of data readout will be delayed by this gradient. So this phase encoding gradient is not really linearly scaled, right? As you can see, the pulse width is kind of changing. Same for the phase encoding for slice direction. So Yeah, this one also is not very widely used recently, but this is very interesting technique, so I included. And then there are certain, after using this variable TE, you can see more signal in the short T2 the region. Term is here, right? Okay, so I went over this basic techniques, technical details, and then let me just quickly go over this morphological UTE imaging techniques. So we don't have much time remaining right now, so I will probably go a little fast. So without UTE and with UTE, right? With UTE, you can definitely see this bone with a very short T2, like around like 300, 200 microsecond. You can see some signal remaining, but the contrast is not very good because they're surrounding long T2 tissues and then bone marrow right here, right? So we want to improve this contrast for better morphological imaging, also quantitative UTE imaging. So there are several techniques. I will just briefly introduce those techniques in this section. So first one is dual echo subtraction technique. So basically, we acquire two images, two different echo time. First one is a very short echo time, like a microsecond, and second one is like a long echo time. And then you have like the UTE signal, right, in the short T2 signal in the short echo time, which decays to the near zero and the late echo time. If you do the echo subtraction, right, then only this short T2 tissues it remains, right, and then long T2 tissues suppress a lot. And then by using this like a weighted echo subtraction, you can improve the short T2 contrast even better. So this example also show that. So there are two echo with two different echo time, right? You can see the tandem signal is gone, almost gone. So if you do echo subtraction, you can see this short T2 tissues in the higher contrast. And if you do like a weighted echo subtraction, you can suppress this remaining signal more, and then you can get better UTE contrast. And then another thing is a long T2 saturation, because this is based on saturation recovery. Basically, you tip the transverse magnetization into transverse plane, and then spoil that the signal, and then you do another your imaging, right, after this saturation recovery preparation, which depends on your pulse duration and then targeted T2. So pulse duration here, and then you have very short T2, then you're here, right? And then your this MXY is almost, there's not much saturation, that means, but your MZ is still remaining. But for the long T2 tissues, MZ, like longitudinal magnetization, is always saturated because to this saturation recovery. And then you only have the long T2, short T2 signal remaining. So this is an example with this is with a long T2 suppression, without long T2 suppression, and with long T2 saturation, right? You can see that this bone marrow and the surrounding soft tissues gone, right? We're using this saturation technique. This is very useful. And also another thing is the off-resonance saturation contrast. So this one also, this is based on the physical physics, the physical basis that short tissue actually has a broad the spectrum. So what we can do is we can apply saturation pulse, and then to suppress like this part, the broad the short T2 spectrum, and then you can do subtraction, right, between those two with and without saturation, this saturation pulse, and then what? So we can get this short T2 signal, the remaining with the fat and water is suppressed. So you can see this UTE, and then with UTE with the saturation, right, of resonance saturation, then you can see that the short T2 signal is very dark. And by doing subtraction, you can actually get this short T2 tissues with long T2 tissue suppressed. Okay, this is another example with this technique. You can see the Achilles tendon in the very high contrast, which is quite good. And then another technique is called the single IR. So IR, I think you already learned in the class, I guess. And then for this one, we typically use it to suppress some soft tissues, including fat and the muscle. And then in this case, we use like some different center frequency tuned to the fat, and then also the affect muscle too. And then here you can get the inversion recovery, and then recovers in the longitudinal magnetization. And then near the nulling point of those your tissues that we want to suppress, we can do imaging, UTE imaging. Then we can get the image with these tissues suppressed. Okay, so you can see that the soft tissues and then the bone marrow are suppressed using this technique. The bone, it has very high contrast, right? Much better contrast for the bone. Also, this is another example. So you can see bone and then some tendon and the muscle, the very short component is in high contrast. Even you can see the coil, RF coil here, right? So this is very useful technique. And this is another example with a different TI, and you can get different contrast because you have different T1 rating and then, right, different suppression. Okay, so another thing is, so now we use the inversion recovery pulse. The first one is to tip the water, right, in longitudinal direction, and then second pulse is just to suppress the fat. And then we can get those two water and fat, longitude to water and the fat signal suppressed at a certain point. And then we can do UT imaging to get the short T2 contrast. So again, this is the dual IR UTE. You can see it's quite nice bone signal with the other tissues suppressed. And another technique is called UTE spectroscopic imaging, UTE SI. So basically, we can get you can use this UTE sequence to get the image in the very small echo spacing with a very short delay. So this delta T is determined by typically data sampling rate, data sampling dwell time, which is in the GE scanner is about 2 microseconds. So we can get hundreds of images. But because there's scan time limitation, we typically here we do undersampling with certain interleaved undersampling scheme. So we can get the hundreds of images here. The scan time is for 2D UT it's around 5 minutes. It's not too long, but 3D maybe takes longer. So this is some representative images, right? Actually, there are hundreds of images, not only 5. But you can see if you go to the late echo, your bone signal decays, right? And then your fat signal is still there. So what you can do is you can put this whole 100 image into one giant matrix, and then we can do in each pixel we can do the Fourier transform. Then you can get the frequency component in each pixel, right? Just like you do the spectroscopy, and then as you can see in the higher frequency domain, there only some artifact remaining because we did like undersampling, right? So only there's a high frequency, the undersampling related artifact. And it's very interesting that you can, in the near the fat frequency, right? And then you can see fat in the high signal. And then the bone, you can see actually the high signal for all the frequency because the bone has broad spectrum. So again, in each pixel, you can get this kind of the spectra. And then you can get T2 star using the line width, right? And then also you can get the proton density using this spectrum. This is very powerful, but for 3D, I think we need more optimization. And then lastly, I will show you some UTE phase imaging. So this is magnitude and this is phase, right? So phase sometimes it gives much better the imaging, the details for certain structure. So like this case. And also, so this is another example for this is a peripheral nerve. You can see in the page, you can see it's much clearer that these vesicles. So which is very useful in this case. Okay, so I am done with what I prepared for today's lecture, and then this is just a list of the quantitative UTE imaging techniques that I didn't cover today. Yeah, but if you're interested in, we'll have the lecture course soon. So you can always join our lecture to see more details about these techniques. And then there's some potential and then application in the clinics. So we have much more applications, and we are very actively working on the UTE imaging. So if you're interested in this, let me know and give me any questions about this. Okay, thank you so much for your attention. And if you have any question, just let me know. Let me check. I don't think any question in the chat. So yeah.
Hey, Hansuk, have people looked at using the U techniques in liver? Because I know there's some interest in looking at the collagen component, or some of the fibrosis that happens in liver. I don't know whether people have been successful, or what are the problems in applying this to liver?
I don't think any problem. For liver, for body imaging, I mean, usually there's not much short component, so I don't think people actually really want to use the UTE imaging. But because for liver, I think I've seen one abstract as an ISMR abstract using the UTE, the ideal. I think it's Scott Leader's group.
Yeah.
Diego Hernando for the ion, right? But for the other tissues, I don't think there's much short component. What's your opinion, Nick? So you think?
Well, I don't know. They do elastography to try to get a handle on the sort of the level of fibrosis in the liver, and I don't know how much sort of short T2 components that involves. I mean, with the imaging we do, it largely disappears, so we wouldn't be able to see any sort of effects of fibrosis. Plus, there may not be that much in terms of the number of protons involved either. But it just seems like a pretty obvious thing to try. That if there were short T2 components with fibrosis, you could correlate that even with the MRE results and sort of validate it. But I'm not sure anybody's tried it.
I don't know. Yeah, but that sounds very interesting, right? The fibrosis, they can have very short T2. There are multiple components, right? So you can definitely benefit from UTE. That's a very good idea.
Or you can use MT. I think people probably tried the magnetization transfer because those more solid components usually have pretty broad line widths. And then there's the question of whether that transfers to the pool that you're actually detecting. So I'm not sure how much MT would. Have you done much with MT in conjunction with the UTE readouts then, or?
Oh yeah. So we do like MT for many projects, right? You know that.
Yeah, so, I know. I just wonder how promising that is, or if they're still struggling to see some sort of effect.
Oh, you mean for the liver?
Well, for any sort of tissues, I guess I haven't followed what you've been doing on the collagen stuff. The tendons and cartilage.
Yeah, then so far it worked pretty well. I think we have many papers actually. The Yajun is the one working on this very actively. So you can take a look at our paper. Yeah.
Okay. Thanks.
Yeah. Thank you for your question. So yeah. So I think Tom posted the online evaluation form in the chat. So after this lecture, after this lecture, maybe this will be gone. So please click this and then finish the evaluation. Any question?
So we have a few. Do any of the I think there's a few students from the course. So I think James and Navid. I know you guys are doing some of the groups are doing final projects. I think they're doing one on UTE. So do you guys have any questions for our speaker? It's a perfect time to ask a world expert in UTE if you have questions, or you could ask him for help on your final project as well. Okay, well, you can always send them an email afterwards.
Yeah, sure.
So I have maybe one last question before we end. So in terms of like MRI hardware, do you have like a wish list? Like, obviously you're using the current, say, MRI, the GE750. Like if you were to design the perfect machine for UTE, what would it be?
Yeah, first, gradient is most important, right? Because
A gradient
again,
strength,
short T2,
right? Or
yeah, gradient strength, also gradient fidelity.
Mhm,
That I think the most important part.
mhm.
Yeah, because the gradient, and also for CTE, also RF power is also very important, because we can get the short. You want to use a short RF pulse as possible to avoid the artifact. We call that slide selection artifact. So otherwise, your readout bandwidth should be kept very low. So if
Right.
you have very high V1 power, then we can use a higher gradient. So that means like you have much faster encoding, and then you can capture more short T2 signal. So yeah, RF and the gradient, those two. And for personally, I'm also interested in the molecular imaging. So like a sodium imaging, right? So for that one, also, maybe it would be great if we have like certain coil, right? We need some specialized coil, so like a dual tune coil or something. So yeah, there are many
Doing
interesting
some sodium
projects.
imaging, right? So you should talk, Nick. I know
Yeah, I
Nick.
think Nick is the expert.
Yeah.
Personally, yeah, but in general, yeah, gradient and RF.
So are you looking at like specialized, localized transmit RX coils so you can have high B1
Yes.
localized area? Okay.
Yes.
So are people
that's
building
good.
those? Are you building those yourself, or who's?
No, we only have very small coil, but not for clinical. We have very small the surface coil, not the TR coil. So, but yeah, I think the for gradient is the most important. I mean, also there are some in the Europe, right? The Prusman group, they are selling this gradient, the measurement, to prove the gradient measurement, the hardware,
Right.
based on like the small
Yeah.
tubes.
Yeah.
And then I think that might be good, right? Because you can measure all the different spatial harmonics of your gradient error. Then it would be very nice for research and for non-Cartesian techniques.
Right.
I think it's about like maybe 100, 200K, something like that, a few years ago.
That's too much, right?
Yeah, that's a lot. But yeah, so I think in my previous school, they tried to get it. They wrote a grant, but I don't know if there are anyone actually buying that.
Right.
It's too expensive. Okay. Yeah.
Well, great. Well,
Thanks
thank
for your
you. Thank you again for a wonderful lecture. And so we will be posting this recording online in our BE280A channel. So thank you again. And obviously fill out the evaluation form. And thank you again. And thanks everyone. And so I'll stop the recording now.